Hi everybody. I'm going to steer clear of the maths. Near-term asteroid mining concepts. You will see in the workshop timetable that I was listed as Asteroid Enterprises. And Asteroid Enterprises was my own company that I set up about 1987. But as Gordon said, DSI in the meantime has incorporated and made its come out announcement a month ago. So that's why the program doesn't actually reflect the details of the situation. Well, last Friday certainly brought everything out to the open, didn't it? It was a marvellous introduction to this conference, and we thank Andrew Dempster and Leonard Bernal for organising such an opening. These things are clearly threat objects, but people like us, Deep Space Industries and Planetary Resources also see these objects as potential resources. And just as a matter of sheer happenstance, the Chelyabinsk meteor variously reported as being about 10 metres diameter or 7 metres diameter or something like that. And anywhere between 6,000 tonnes and 17,000 tonnes is in fact about the size object that both the Keck study and our own study showed can be moved, can be deflected by spacecraft which are essentially modified geostationary satellite buses, provided those buses could get there and dock with them and meet the Delta V requirements. Resources of Near-Earth Space. I'm purposely using that title because that's the title of the classic text edited by Professor John S. Lewis from the University of Arizona, who many of us would regard as being the father of asteroid resources studies. The resources of Near-Earth Space include, of course, sunlight, raw regolith gravel, that's a resource, potential resource, reduced metal, metallic metal, magnetite, oxidized metal, water, gases, CO2, methane, and other gases, volatiles. Kerogen, asphalt, the carbonaceous chondrites have these matrices, this matrix of complex carbonaceous material. Platinum group metals, which get a lot of airtime in the mainstream media, and silicon. The locations that we're interested in are the near-Earth asteroids and comets, and we don't want to exclude Phobos and Deimos, and of course use of resources on them and building a base on Phobos and Deimos would be a serious enabling factor for colonisation of Mars and transport to Mars. Asteroid characterisation, what do they look like, how big, how many, what structure and strength, why are we interested in them? It's fascinating to me. I started looking into this sort of stuff seriously in the mid-90s, how little we knew, how very recently, and even now we have only very few images of asteroids. That's the smallest asteroid that we have visual imaging of, and Itokawa, as we've been told already, is about 500 metres from that end to that end. Nobody knows how small you go and still get asteroids that are rubble piles, collections of boulders draped with regolith. Is it 100 metres? Below that, at what point do you get so small that you merely got rocks that are bare, single lumps, like a big lump of rock from a basalt quarry? We don't know. There's lots of things we don't know about asteroids. Here are some images, and I purposely include Comet Builder there because it almost indicates how you have this continuity or this spectrum from things which are blatantly cometary to things which are blatantly asteroidal, and there's a whole range of asteroids. The D-class asteroids, where the question is, what's their origin? Are they in fact extinct comets? And so we've got a range of materials, we've got a range of potential properties of the regolith. We're getting new knowledge all the time. The rate of expansion of knowledge with regard to asteroids is just amazing. Congratulations to the Chinese for their recent successful close flyby in late December last year of the NearEarth Asteroid 2 targets via a repurposed lunar probe. Zhang'an 2 was moved from a lunar orbit to an Earth-Sun L1 position, and then moved from the Earth-Sun L1 position to a transfer orbit to do a fast flyby of 2 targets, about 7 million kilometres away from the Earth. The relative velocity at the flyby was about 11 or 12 kilometres a second. It was very fast, and the first reports were that they only missed it by 3 kilometres. But the more recent reports are that the missed distance was about 90 kilometres, which is still pretty damn good shooting. The discovery rate of near-Earth asteroids has gone up dramatically with the success of various search programs. And we now have, as you see on the graph there, 9,500 known near-Earth asteroids. The large NEAs are the nominally plus 1 kilometre diameter ones. The discovery rate's fallen off. Why? Because we've basically found them all, almost all of them. The threat of another Chicxulub tertiary Cretaceous major climate disruption event, such as killed the dinosaurs, from the 1 kilometre plus asteroids is basically gone away, because we know where they all are, and we know what their orbits are. There might be another one or two to be discovered, but the threat of the really big impacts has been retired, so to speak. But there's lots and lots and lots, of sub-kilometre objects that have not yet been found, as we saw on Friday. So there's a huge increase in potential targets. Near-Earth asteroids, known now, approximately 9,500, I just said. Those greater than 300 metres diameter, known, 2,900. Those greater than 1 kilometre diameter, known, 850. The potential for this number to increase and increase, it's just going to keep on going for a long, long time. So we're getting more and more and more potential mining targets. The number of NEAs that are more accessible than the Moon is presently about 1,700. The number of potentially hazardous asteroids is presently about 1,300, and that number is going up as well. And it's interesting that the potentially hazardous asteroids are those which come within about 7.5 million kilometres of the Earth orbit grazing perhaps, and that makes it relatively easier to return payloads from them to Earth orbit. So the PHAs are not only the threat objects, but they are also the first easiest potential resource objects. Asteroid structure and strength. We have seen from pictures of different of these bodies that they are all covered by a deep regolith, a gravel sand layer. They all appear to be heavily fractured or quite blatantly rubble piles. The indications are of large void spaces. Dr. Yano spoke about the idea of there being these macroscopic voids between giant boulders at depth in Itokawa, and showed these very, very tempting drawings, cartoon drawings of how the void spaces might be there, explaining the very low density that they found in these developed. Many appear to contain water in clays or salts and or asphalt-like material and or nickel iron metal and platinum group metals and silicates. This information comes from two biased sources. One biased source is the source of information from that which lands on the Earth, meteorites. Why is that a biased source? Because the more friable objects and the more volatile objects don't survive passage through the atmosphere. So there is a biased source there in meteorites that pick up off the surface of the Earth and analyse. The other biased source of information is spectroscopic information that is obtained by telescope, by astronomers. That's a biased source because it can only give you information about the top micron or so of the surface, because light doesn't get out from deeper than that. So, but both of these biased sources of information do suggest these sort of compositions. So we've got an extremely diverse range of objects in terms of their compositions. And within individual objects, you've got potentially extreme diversity of different compositions. Interesting stuff. What are the potential products from asteroid mining? Well, they jump out at you from that earlier list. Raw mass, regolith, can be used for ballast in a tether sort of situation, and can be used for radiation shielding. Somebody mentioned radiation shielding. It's been mentioned 2 or 3 times. Water and gases can be used for in-space propellant and for life support. Nickel iron metal can be used for in-space construction. Platinum group metals for export to sail on Earth. And silicon for space photovoltaic arrays. All of these are potentially, given the circumstances, potentially products. Potentially products. And considering that the current cost of mass used in geostationary orbit is of the order of $20,000 or $30,000 or $40,000 per kilogram. Considering the present cost of mass used in LEO orbit is of the order of, pick a number, $4,000 a kilogram, $10,000 a kilogram, anything that can be extracted from asteroids and brought back to Earth orbit and provided in usable form in orbit has a potential value similar to the launch cost of the material that it's replacing. Okay? Conceptual process flow sheets. Here I start treading into shaky ground, don't I? We really don't know anything very much at all about these things, but we clearly have to develop a portfolio of methods for anchoring on these objects. You have to develop a portfolio of methods for excavating the regolith or otherwise collecting mass off these objects. Then contain the mass. Then crush, size separation, magnetic separation to get out your metallic metal and your magnetite. Bake to remove the volatiles, condense to collect those volatiles. That's the sort of conceptual process that needs lots and lots and lots and lots and lots and lots of work. Here I flick over into Mining Engineering 101 for space miners. John spoke about it earlier. What is ore? Material is ore only if you can mine, process, extract, transport to market and sell it and make a profit. If the material can't support a commercial enterprise, if it can't make a profit for the mining and processing company, it ain't ore. Mine project planning involves choosing between competing mining and metallurgical extraction concepts so as to minimise capital expenditure, minimise operating cost, minimise payback time, minimise project risk, and thus maximise expectation net present value. That's the logic which is used in identifying mining project concepts here on Earth and choosing between different alternative concepts. It's not a straightforward situation. People not in the mining industry think that you just find an ore body, dig an open pit and sell it. Well, it mightn't be amenable to open pitting. It might be better to do an underground mine. If you're going to do an open pit in the wet tropics, your water catchment area is too big. You might want to go underground to minimise your water catchment area and minimise the environmental impact. There are choices that are made in defining your project that have to be taken very carefully and step by step. And the same is going to apply a fortiori to space mining projects. What is ore? Here's a picture of the ERA range of uranium mine in the Northern Territory. They were mining up until about 2 months ago, 3 months ago, 4 months ago, 0.25% uranium. They've finished their open pit now. They're backfilling. They're drastically exploring like crazy to try and get to decide whether they're going to go underground for a future range of deeps. The value of that ore is $250 per tonne of ore excavated, defined by the market. Ore is economic mineralisation. Here's a picture of Prominent Hill Copper Mine, South Australia, 2% copper, 0.2 ppm gold. About $170, $200 per tonne, something like that, on Earth, but worthless in space. The value of an ore depends on where you want to use it. The value of extraterrestrial materials, I would maintain, is driven largely by the launch cost of working for delivering it to the location of use in space. Present launch cost to LEO, 4,000 plus bucks per kilogram using Elon Musk's Falcon 9. Present launch cost to GEO, about 17,000. It can be as high as 30,000 or 40,000 or more. We in DSI tried to make some sort of guesstimate of what those costs might be in 2020. And if SpaceX's Falcon 9 Heavy goes ahead, that would give something like a threefold reduction in launch cost to LEO. And if his partial reusability idea goes ahead, that would give something like another threefold reduction in cost, we assess. So in our planning, we have to assume that we have to come in under that sort of cost per kilo to LEO, and maybe 3,000, maybe 4,000, somewhere in there, sort of cost for delivery to GEO. It's an economic constraint we have to meet. And if we don't meet it, we don't have a project. So, let me recap. The value of asteroidal regolith, if you've got a typical target body which might contain 50 ppm platinum group metals, 10% nickel iron, 10% magnetite, 10% water, and these are reasonable numbers. These are reasonable numbers for ordinary stony meteorites, L-class ordinary chondrites, and for a number of subsets of carbonaceous chondrites. These are reasonable numbers. If you take these reasonable numbers, they equate to giving a typical ton of asteroidal regolith a potential value of over $1 million in orbit.
Is that against the 2020 number?
Yeah, it's against the 2020 number. Much higher now. Okay, much higher now. For its water and nickel iron content. But only 4,000 bucks for its platinum group metals on Earth. People don't, you've got to stop and do the sums. Right? You've got to stop and do the sums. $1 million a tonne is very high value ore. Mining engineers in the room? How many mining engineers in the room? Is that right? Extremely high value ore, isn't it?
Where's that unobtainium?
Unobtainium.
Unobtainium, close to unobtainium, very close to unobtainium. So it's extremely high value ore. So resources valuation in an actively developing in-space market. Here's a new vision for you. Virtually all asteroidal retrieved mass will have some value, driven by the current Earth launch cost, if it can be fabricated into usable form. We've got metal, we've got regolith, we've got volatiles. If the volatiles can be turned into propellant, if the metals can be turned into fabricated sheet structures, if the regolith can be bagged or welded or sintered or turned into radiation shield, simply bagged, it's got value. That helps us when it comes to JORC compliance stuff and Canadian N43-101 compliance, things that where people like us, Jonathan and myself, will have to end up saying we believe there's such and such a value in this material. If I can say 90% of the stuff we bring back will in fact be saleable in some form or another at some minimum, that helps. So the value proposition is that NEAs are numerous. Approximately 10% of them are more than 10% of them, closer to 17%, something like that, are more accessible than the Moon. The majority, not the minority, not the tiny minority, not 1 in 1,000, but the majority are potentially prospective for water or nickel iron. Very valuable ore, more than $1 million per tonne, looking out even to the lower cost structure of 2020. Easy extraction, potentially, there we know. We've never extracted material in zero G vacuum. But those are not difficult extraction tasks that I described earlier. So, bingo. Asteroid resource missions will be similar to short campaign mining of remote, very high value ore bodies. It's not a large commodity, scraping away to get the lowest possible cost structure from the big iron ore mine. No, it's remote. It's mining, short campaign mining of remote, very high value ore bodies. 5 minutes. Here are some terrestrial examples. The Klondike Gold Rush, 1898, 1899. 100,000 people went to the Klondike Gold Rush. Some of them made a lot of money, a lot didn't. My radiation background prompts me to tell you that in the 1920s, radium was worth $100,000, $200,000 a gram in dollars of the day. So the 1920s radium mines were indeed very remote, very, 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 very high-grade ore. You think Shinkolova in the Belgian Congo, you think Port Radium up in the Northwest Territories of Canada, you think Radium in South Australia and really remote places. Genuinely life-threatening places. The 1930s airlift supported gold bridging of Bololo in New Guinea. There were 8 2,000-tonne gold bridges that were flown in 5-tonne bits in 3 Junkers trimotors and 2 hydro power plants and a sawmill and the wherewithal for 3 towns. And between 1930 and 1940, the biggest airlift in the world, bigger than the next 5 biggest countries in the world, France, US, UK, Canada, Spain, I think, or Germany. There was more tonne miles flown, or tonne kilometres flown in New Guinea than everywhere else in the world. And the 4 biggest lift airports in the world were Lae, Bololo, Wau and Salamoa in New Guinea. Unbelievable. And when I see that, I see these pictures, these old Junkers trimotors, I think of Elon Musk's Falcon 9 Heavy. The Cardi Diamond Mine in Canada sees on 10 weeks access by ice road per year. You look at the logistics. The logistics of these sort of things aren't that different from the logistics of getting in space. Namibia offshore diamond dredging, very high-grade material. Deep sea black smoke or massive sulfides and anomalous minerals are chasing 50% metal, and these 1.5 kilometres below the seabed, black smoke is from volcanic peaks. Remote. Can't get divers down there. It's 1.5 kilometres down. It's 150 atmospheres pressure. Artisanal gold mines in Brazil, Indonesia, the little family mines that John was talking about before lunch. These are sort of remote, high-value mines that are the more likely parallels with what we will be envisioning for the Moon and for asteroids, I believe. Pathway to commercialisation, flyby missions, rendezvous and assay, sample return and bulk. That's our pathway. First one is the flyby missions, with little CubeSat style 12U for quick flyby for imaging. Then Dragonfly missions for rendezvous and surface science, and then later rendezvous surface science and sample return. Materials collection, we've got a lot of work to do there. As I said earlier, we have to develop portfolios of these different approaches. The new concept was the bag and capture of small meteoroids, 5-metre diameter things, and the Keck mission study came up with that, and we simultaneously came up with the same thing when they published themselves. But stole our idea. But they hadn't. It was merely convergence. Which technique we'll be pursuing, too early to say, will depend on details. The target body must be robust. The takeaway messages are these: high and increasing discovery rate of NEAs, many contain easily extractable high-value products. Access to NEA resources is technically within reach. We will develop the means to tap asteroid resources and also mitigate the impact threats. I mean we, as an entire community, we believe that the NearEarth asteroids will be major resource opportunities in the 21st century. And that, I think, ladies and gentlemen, ta-da, is it. Thank you.
Questions for Mark?
Mark, it's great to see that $1 million for a pump, I guess. But as you know, as we are mining engineers, segment which I like to hear the net present value.
You'd like to hear?
Net present value of the project. Have you done any calculations on that?
Well, I did in my thesis net present value calculations for a series of missions. This was one of the missions which I discussed in description. This type of mission is one which I discussed in description in my thesis, but did not work out the NPV, because at that time there weren't enough targets of that class. But it is clearly relatively straightforward in principle to calculate that net present value, because it will depend on the mission time, the timeline. And the timeline, it will depend on the type of orbit that the thing is in and how. Yeah. So we know the timeline. We need to find out what the processing costs will be. But yes, we're aware of the net present, and more importantly than net present value, expectation net present value, because we've got to put in statistical surety of full or partial success as well. I agree. NPV. NPV is a driver. NPV actually drives the choices that we make. Propulsion choices, processing choices, what the product is. NPV drives.
Question all the way in the back.
Yes. Thanks. You're using the launch costs of materials in order to give your value of materials per ton. But what happens when there are 2 or 3 different suppliers in space and competition between them brings the cost of these materials below what the launch cost of material is?
Well, it'll hurt the individuals, but it'll be great for humanity's movement in
I'm
space.
just wondering, have you actually thought about that in your calculations?
It's too early. It's far too early.
Here's another horrible, probably too early question. You're talking about raw materials being used in situ on the moon or in orbit, right? But we send up very few raw materials to space for any purpose. So manufacturing in orbit is an entire other section that has been less developed even than asteroid mining, and maybe needs to be discussed before we start dealing with asteroid mining.
Yeah, I have a couple of, I agree, but a couple of comments on that. There are already bids out, and I think MDA was, or McDonnell Douglas, or one of those, or maybe it was Hughes, was seeking bids to deliver propellant to geostationary satellites. Now, admittedly, they were seeking bids to develop to transport hydrogen, which is not an obvious product. But the fact that private companies are seeking expressions of interest to develop propellant, to bring propellant, to purchase propellant in orbit, is a glimmer of hope. It's also clear that ISS uses something like 60 tonnes of water per year. Right? And I had initially thought that our interest of some of my colleagues in 3D printing of metal was a tangent. But if you say 3D printing of metal to make immediately usable parts or structural objects, sheets, beams, pipes in space, then that opens that up as well. So yes, it's the market and the project development ideas enable one another. And a large part of the uncertainty of all this is how fast will such a market develop.
Another too early to tell, but if you're going to start dismantling even small bodies in some Earth orbit or other, you're going to have some very safe way of disposing of the waste material. Otherwise, you're going to make space completely unusable through the debris.
Let's hope that the amount of debris is minor, because it will all have some use.
Yeah, but I mean, if for example, only, well, say initially, water, if water is perhaps the most likely one to be able to be marketed initially, then you're going to have a whole lot of leftover material, yeah, which will be useful at a future stage. So you'll actually will want to have it contained.
We don't want to throw it away. I mean,
no.
One thought that occurred to us, if we were going first off for water or other volatiles for propellant, what do we do with the baked out soil? And one of our colleagues came up with the idea, well, we bag it and we can sell it for radiation shielding, or, I know, an even better idea, let's hire it out for radiation shielding and then take it back when we want to process it again.
I'm going to use my privilege as the chair to ask a question, and then I'm going to take a question from Hirose, and then there's one in the center there. So my question is, we've heard a couple of different people with views on the legal aspects.
Yes.
most recently this afternoon, there was the view that a proper legal environment is essential to make this work. What's your take on that in the context of what you talked about?
I think the DSI as an organisation is agnostic at the moment. We don't know. I think my own field is I'm a keen reader of mining history, and you know, you read the mining history of the Klondike, you read the mining history of the Ballarat Gold Rush, you read the mining history of the California 49ers, and in almost all those cases, people went and started prospecting and mining before there was a clear-cut legal regime, and you built around it. But that's me, not DSI. I think DSI would say, well, wait and see. And of course, when there is a legal regime, then a corporation has to follow, obviously.
Hi, Jimmy.
Yeah, okay. I tend to be a problem of today, not the future. Okay. I'm just wondering about your comments on the gap between the sides, which we're currently able to observe and track and maybe do some spectroscopic work on NEO against the size of the Keck study, which is whole asteroid return. I think the Keck study is targeting around 1 or 2 meters size.
Well, I thought it was a bit bigger than that, you know. I thought it was of the order of 5 meters or something. It depends on the accessibility, the delta V accessibility of the orbit that the object is in, and how easy it is to get back to our lunar swing by. But my understanding was that 3 meters, 5 meters, maybe as big as 7 meters were the sizes of the bodies that were being considered for being grabbed. And if you look at the image, that basically fits with that. Now the image of the bag capturing the rock.
I understand that portion, because the Keck study is logical only if we can find suitable, accessible asteroid of a suitable size. But the difficulty I'm facing is that our telescopic capability is still limited.
You're right. The difficulty is
small enough asteroids and looking for lots of orbits. So just like the Notion event you just showed earlier, that was 15, 17 meters across. And coming from the sun side, we have found it.
the big threat to this grab a meteoroid in free space approach is indeed that they're too small to see. I agree with you. And you're almost purely by accident that you'll find these tiny, tiny rocks.
Last question there.
So the platinum group metals seem to be the only one, so the only product that we're going to be able to sell to an Earth-based market rather than like something to build further infrastructure in space. How would you actually make that platinum available to an Earth market? Would you be just like throwing it into a desert somewhere on the Earth, or like?
Our Japanese colleagues have proven you can aim it at Wummer and you'll land somewhere nearby. But no, the answer is one would have to engineer re-entry capsules, and one would have to go through the entire permitting procedure of getting an agreement for where the landing spaces would be, etc., etc.
Let us thank both of our speakers, Dr. Held and Mark.